Okay, thank you very much. And I'd like to thank at first organizers to arrange such a great session. And then I feel really honored to speak here. And today I'd like to talk about how important cloud and aerosols are in our climate, even though they are just a tiny fraction in the mass. And also I like to talk about how recent satellite observation can be used to advance the science of cloud and aerosols in terms of the climate modeling. So now let me just start with this very simple picture of our Earth looking from satellites from space. One is with clouds and another is without clouds. And that highlights that how clouds makes a difference in appearance of our Earth. And basically the clouds make our Earth whitish, very simply speaking. And then that means that the clouds has a profound impact on the sunlight received by our Earth. And that kind of problem of the cloud and the cloud impact on climate is very well described by their radiative impact. That means the clouds impact on the radiative energy flow in our atmosphere coming from the sun and coming from our Earth. And there are basically two impacts that clouds have on the radiation. One is the basically cooling effect for the solar radiation. That was basically blocked by the clouds. That has a cooling effect. And another is the warming effect that absorbs, by which the clouds absorb the terrestrial radiation escaping to the space. That basically the clouds prevents the terrestrial radiation or thermal radiation escaping from the Earth. So that is so-called greenhouse effect of clouds. And through these two profound impact of clouds on Earth radiation, they have a profound impact on the global energy and water budget. But there's another fact that the cloud water represents only a very tiny fraction of the total water mass on Earth. That's about only smaller than only about the 0.01% in terms of the mass fraction of the total water on the Earth, including ocean and the ice sheets. So this actually represents the difficulty, fundamental difficulty of representing the clouds, particularly for predicting our future climate change, and also for understanding the cloud impacts on the climate, because of this very tiny fraction of cloud water that has to be predicted very accurately because of its profound impact on the global energy and water budget. And such a difficulty is represented by the well-known problem of the cloud-climate feedback. That means that it is still pretty much unknown if the clouds are accelerating or damping the global climate change, for example, global warming induced by the greenhouse gas emissions. And shown here is the just a highlight from the very recent studies or analysis looking at the state-of-the-art global climate models in terms of the so-called feedback processes that complicates the climate responses to a given, for example, greenhouse gas emissions. And the cloud is actually represents the largest uncertainty among various feedback mechanisms. And that's still a major challenge even in the latest generation of climate models. So that's why we need to study cloud in more detail. And to that end, we basically have to dive into the very detailed things in the clouds. For example, trying to understand how the cloud droplets are formed and how they experience the growth processes and eventually to form precipitation. And such a very kind of a macroscopic, microscopic picture of the cloud has to be better understood to predict the macroscopic impact of clouds, like I shown in the previous slide here. So that's kind of a fundamental difficulty for cloud study in the climate, because we have to care about the both microscopic and macroscopic aspects of the cloud. And another difficulty is that such a cloud formation and its precipitation formation eventually is a highly nonlinear system in terms of physical systems, with a kind of a threshold particle size when the precipitation to happen. And another another complication of this cloud thing in the climate is the cloud particle is not just formed from pure water vapor, but also it requires the other foreign particles like aerosols as a nuclei or seed to form the cloud particles. That means that the aerosols or minute air pollutions can change or can modify the cloud properties and the precipitation characteristics, and eventually have a profound impact on the climate. And such a air pollution effect on clouds are very simply schematically shown here, illustrating how there are different aerosol conditions, like very clean condition and the polluted conditions with different aerosol or air pollution conditions, air pollution concentrations. The clouds have largely different characteristics. And then in the case of very clean clouds with very small number of air pollution particles, clouds can become relatively large because they can grow faster, because only a smaller number of particles can compete with each other to absorb the water vapor. But in the case of very polluted clouds with a larger number of aerosol particles, that means that there are much more cloud nuclei that can form the cloud, so that the more numerous clouds have to compete with each other to absorb the water vapor. So as a result of that kind of processes, such a difference in the aerosol or air pollution can cause very different characteristics of clouds that have actually very different effect at first for the radiation. That means that the more polluted clouds tends to be more reflective to sunlight. So that means more by the polluted clouds, because of the each cloud particle became smaller, and then it takes much more time for them to grow into the precipitations. So these very simple mechanisms actually have a profound impact on the global climate. But these aerosol particles also have their own effects on the radiation, for example, the sunlight. And for example, so-called white color aerosols like sulfate aerosols have a cooling impact on the Earth because they can scatter the sunlight very effectively. And on the other hand, there's another kind of aerosols like black colored aerosols, for example, black carbon, that has a warming impact on the climate. And actually, there are fundamental uncertainty in estimating how these different types of aerosols have an effect on our climate. That's something like highlighted in this right-hand side. in terms of the radiative forcings, that is the energy budget imbalances caused by these aerosols. And according to our current knowledge, the net effect from all of these aerosols is likely cooling. That's largely because of the clouds change, like I've shown here, is the major contributor to the cooling impact on the Earth. But there are still large uncertainties, particularly for the aerosol particles that have relatively short lifetimes in the atmosphere. But the story is actually even more complicated because such cooling and warming aerosols is not just decreasing or increasing the temperatures, but the magnitude of the temperature change is also largely different depending on the aerosol types. And for example, here shown is the temperature response, global mean temperature response to the emission change of, for example, black carbon and sulfate is pretty much different. And the black carbon has only a weak impact on the global mean temperature. That's also found in our recent simulation with our using our MIROC climate model. So this has a very important implication. For example, for considering the global warming mitigation, that's basically considered for the CO2 and greenhouse gases, but there is also a possibility to mitigate global warming by controlling these aerosol particles, but there is still a large uncertainty in this kind of argument. So we need to better understand this kind of thing. And to that end, fundamentally important is we need to quantify global energy budget, basically. For example, these warming aerosols and cooling aerosols have the impact on the global energy budget. And for the purpose, we need to understand the kind of a whole picture of the global energy budget changes, including lots of different components like highlighted here. And this is just actually a model-based estimate using our MIROC model that was simulated for the different energy balance components change in response to the black carbon was changed. And so there are a bunch of numbers here, but these are just model-based estimates. And there are actually several uncertainties assigned to each component of this energy budget. And among others, there are some key uncertain issues, for example, in this picture of global energy balance. One is how the aerosol, for example, black carbon, can heat the atmosphere. And another is how the cloud and the precipitation can respond to such an aerosol forcing or heating in the case of black carbon. And eventually, we need to understand how the whole picture of global energy budget can change in response to the aerosol forcings. So this is kind of our ultimate goal to better quantify this kind of energy budget changes for a given climate forcings due to like aerosols. So there are a bunch of uncertainties in this picture, but one of the most uncertain and the most important is the aerosol-induced change of clouds that I mentioned in the previous slides. That actually has a significant cooling impact on the climate, as I mentioned, and that can be highlighted in this simulation results of the historical temperature change for the past 150 years, showing that how the global mean temperature has been increasing, basically due to the greenhouse gas warming. But there is another counter-cooling impact by the aerosol-induced cloud changes that is actually highly sensitive to the highly sensitive to the model assumption of cloud actually. So that means that the how the cloud is cloud particle is assumed in the model largely affects this magnitude of the cooling impact, and then that leads to very different scenarios of global mean temperature trend, and some of them can match to the observed temperature trend, but the others does not match to the observed temperature trend. So we need to reduce this kind of fundamental uncertainty in the model to better represent the global warming trend and then the better future prediction of climate change. And for that purpose, it is very powerful to use the observation information, of course. And the recent progress, recent remarkable progress is the progress in the satellite observations that now has the this kind of terrain type measurement, including lots of different satellite platforms and satellite sensors that can now look at the different aspects of the same target, like same cloud and precipitation at the same time, so that the different aspects of the same cloud can be combined, for example, to better characterize the whole system of the cloud and precipitations. So this is a major progress in the recent satellite observations that can be used to improve and evaluate our climate modeling and eventually climate predictions. And thanks to this kind of progress in satellite observation, now it is well known that how the clouds are suspended in Earth's atmosphere. And shown here is just a simple zonal picture of the cloud occurrences and the precipitation occurrences as a function of height and latitude. And also now we know that the what is the cloud suspended atmosphere like that is liquid to ice or mixed phase. So now we can use this kind of information from the new observations to better evaluate and improve the climate models and climate predictions. Okay, so I will skip this. And then among such a model improvement activity, the most fundamental thing I think is the looking at the fundamental microscopic cloud processes on the global scale from the satellite observations by making some kind of statistics combining different satellite variables. And shown here is just an example of how the rain forms from cloud that's now found from the observation data. And now we can use this kind of information to better evaluate the climate models. And here is just one example for that kind of model evaluation using the satellite observations, showing how the observation statistics can be used to improve the corresponding model statistics of the rain formation process, for example. But if you do this kind of model constraint using observations, that has actually another secondary impact on the global energy balance, for example. And in this case, the aerosol-induced cooling impact became too much cooling, too large because of this model adjustment. So that means there still exists the error compensation in different components in the model that's now exposed by this kind of new satellite observations. And as a result, the climate simulation, for example, is now better, should be better constrained by this observation information. But as a result of such a comparison, the scenario that can better represent the global warming trend is actually based on the wrong assumption of the cloud processes based on the satellite observations. So that means that the current climate models fail to represent the fundamental link between the microscopic cloud and the macroscopic climate. So actually that's the problem. So that means that we need to advance our climate modeling in more fundamental way by looking at the cloud processes and its impact on the macroscopic climate. And the fundamental problem in the current climate models is its very coarse grid resolution. That's only about 100 kilometers, and that cannot resolve individual cloud precipitation and convection that happens over around 1 kilometer scale. So we need to take into account this kind of so-called subgrid cloud inhomogeneities for better accounting for the microscopic cloud impact on the climate. And now we are also using the satellite observation for the purpose, trying to reduce our model errors by correcting this kind of, by accounting for this kind of effects. And here is another example of our recent model progress, improving the precipitation processes, again using the satellite observations. And our new prognostic precipitation modeling can represent the better picture of the total cloud ice distribution over the globe that's closer to the satellite observations. And actually, based on this, based on these model progresses, now the fundamental problem that I mentioned in the previous slides, pointing out the model compensation errors, is now largely reduced by this kind of new development. And showing here is just a highlight of the results, but I don't go through the result here because they are just complicated. But the main message here is the new improved model, particularly for the cloud and the precipitation processes, supported by satellite observations, can represent both the rain process and aerosol cooling impact realistically. And this is enabled by the more sophisticated representation of cloud processes that's informed by satellite observations. So that's, I think, one of the major progresses recently based on the combining modeling and the observations. But actually, we are now entering the new era of global modeling by emergence of the global cloud resolving model that has a much higher horizontal resolution that now can resolve individual clouds. And that actually, that is actually turned out to represent the very realistic cloud responses to aerosol changes that's much closer to satellite observations compared to the traditional climate models. But so far in this presentation, I've focused on more like the only liquid phase clouds actually, and then the warm rain formation from the clouds. That's actually the easiest part of the whole spectrum of cloud and convection existing in the Earth. But now, thanks to the satellite observation advancement, we can also start to look at the how the more complicated clouds, like mixed phase clouds, including both liquid particle and ice particles, how these clouds are distributed on the global scale, and how these clouds have different microscopic structures and its relationship to some different cloud heights. But there is still a missing information here. That's how these cloud microscopic structure relate to the cloud dynamics, and then the what is the radiative effects of these different clouds. So more advanced global measurements of clouds are required. So now we are we have a plan of the upcoming new satellite measurements with the enhanced new capabilities that can address part of these remaining issues. For example, by measuring the updraft velocity in the cloud by this new Earth-Care satellite missions. And there is also another ongoing study in the NASA ACCP, Aerosol Cloud Convection Precipitation study, that also can enhance the satellite observations to advance our understandings of cloud and precipitations. So okay, so this is almost time. So yeah, I like to stop here, and this is just a summary left for your viewing. Yeah, thank you very much.